capacitors into a 48-volt system, but I will give insight into where they are used, why, and what products to look for. We'll talk about power issues in EVs that can be solved with supercaps. Then I will give an overview of supercapacitor technology and show some of the applications where they've been designed in. So why are car designers going to 48-volt systems for the low voltage bus instead of continuing to extend the 12-volt bus, which has been in existence almost from the start of cars? With 48 volts, they can improve efficiency with lower current. And with lower current, they can also save on cabling costs with smaller gauge wire. The higher voltage also makes high power components more efficient. As more and more components are attached to the 48-volt bus, it becomes increasingly important to maintain control of the bus voltage. When turning the car, the steering system can pull high power, and this can reach kilowatts of power near the end of its travel. Air conditioning compressors and braking systems also pull high power when activated. Further, with the advent of brake-by-wire and steer-by-wire, if the high voltage battery is disconnected or depleted, these systems will stop functioning and create a safety hazard. Let's talk a little bit about what a supercapacitor is and how it functions. It is a rechargeable energy storage device like a battery, but with different properties. If I can make an analogy to a tank of water representing energy storage, a capacitor has a small volume but very large faucets, meaning they can charge and discharge very quickly, but do not hold a lot of energy, for example, to try and drive a car long distances. They can also charge and discharge almost an unlimited number of times. Batteries, on the other hand, are a very large tank, meaning they hold a lot of energy, but relatively small faucets, so they are limited in their charge and discharge rates. You might ask how batteries are used as the main energy source for driving in EVs if they don't have much power. In this case, it's power relative to the size of the tank. Since we all want more and more range on one charge, the battery capacity is very large. So the small faucets in total can still provide a lot of power for acceleration and recover energy from braking. Back to supercapacitors and how they function, there are no moving parts or chemical reactions. They're very safe with no thermal runaway concerns, no rare earth metals, and primarily made from carbon, cellulose, and aluminum. Looking more in detail at how supercapacitors operate, I'll first say ultracapacitor, supercapacitor, and EDLC are all industry terms for the same device. They are made from two activated carbon electrodes, with most of the carbon in the industry made from coconut shells. They have very high surface area to get very high capacitance compared to other types of capacitors. There's a liquid electrolyte, which when charged, the ions are attracted to the surface of the carbon. You can see from the diagram that when this occurs, all of the charges align on each surface. There are two electrode plates of carbon, and then the ions form more electrode plates. In essence, there are two capacitors in series. When discharged, the ions distribute back into the solvent and the capacitance drops. One of the design challenges is that voltage drops as the capacitor is discharged. We need to design the right capacitance to stay within the voltage limits of the system, or use a DC to DC converter with the capacitors. In contrast, batteries depend upon chemical reactions at each electrode surface. Lithium-ion batteries have one electrode made from graphite and one that is a metal oxide. When discharging, lithium reacts at the cathode, and when charging at the anode. In both cases, it's a chemical reaction which depends heavily on temperature, and the reaction has a limited rate at which they can occur. This is why their faucets or charge-discharge rates are smaller. You can see in an idealized constant current discharge, the voltage profile is more flat than a supercapacitor until it gets near the end of its capacity. Why are supercapacitors used? First, they are very high power, up to 100 times that of a battery. This allows them to be sized in terms of energy to the application and not require oversizing to meet the power requirements. As we've seen on the previous slides, they are less dependent on temperature in both performance and lifetime, so they can be placed around the car and closer to the loads that they support. This allows designers to reduce the cost of cabling. The higher power also means higher efficiency. Since there are no chemical reactions, they can be charged and discharged millions of times so they can last the life of the vehicle. As noted earlier, they are very safe and ideally suited for short duration charges and discharges. Let's look at a few applications where supercapacitors are either designed in or being designed into 48-volt systems. The first is board net stabilization. All components on the 48-volt system have a voltage range that they are designed to operate within. But if one component pulls a lot of power or several components pull peak power at the same time, the voltage can drop below the minimum voltage, typically 40 to 42 volts. You might ask, why not just pull more power from the main battery? The answer is that OEMs want to keep as much power and energy for driving as much as they can and not devote it to other subsystems. Furthermore, there can be delays in transferring the power from the 400 or 800 volt main battery and not hold up the voltage on the 48 volt system in time. Supercapacitor module can be designed to keep the voltage above this 40 volt or whatever the minimum voltage is. It is typically designed to provide less than 3 kilowatts, something more along the lines typically of 1 kilowatt. The voltage drop is normally very quick and transitory, so it can be for milliseconds to a few seconds. This is ideal for supercapacitors. While the supercaps provide power to the whole system, they normally come into play when something like power steering or braking are at their limits. There are different approaches to the supercapacitor design. In some cases, the supercapacitors are sized to support a maximum power level and discharge time with no DC to DC converter. But most designs use a DC to DC converter to utilize the capacitors more fully or reduce the number of supercaps and boost the voltage to the required level. So we can see anywhere from 4 to 18 cells in the 350 to 400 farad range, although we have seen some designs that might use just 2 cells but at 1,000 farads. It really comes down to a balance of power, energy, and of course size and cost. Here's an example of a power steering power profile and its effect on the board net. The blue line is the motor power. You can see that it's normally very low when the car is going straight. But then when the driver turns, you can see up to 1400 watt peaks for less than 2 seconds. This causes the 48 volt bus, shown with the green line, to drop from 52 volts to below 40 volts. Supercapacitors will shave the 1500 volt peak and limit the voltage drop. It doesn't need to shave an entire 1500 volts, but just part of it to keep the voltage above the minimum. The next application we'll look at, and we're starting to see more and more, is active suspension. In this case, the system functions to keep wheels in contact with the road as they hit bumps and potholes and other low points. There are motors in the suspension to drive the wheels down on a drop or absorb energy in a bump. The driving experience is improved as the wheels stay in better contact with the road, as well as efficiency of the overall driving profile being improved. In this case, the supercapacitor module is connected to the suspension motors, completely independent of the normal 48 volt bus. The system control occurs at up to 500 Hz, so local power storage is needed. The number of cycles makes batteries not an option. We've seen motors that work over the natural supercapacitor voltage range and some that require a DC to DC converter inside the module. For the most part, all designs are using 18 cells in the 350 to 400 farad range. The last application that I'll discuss on the 48 volt bus is for backup power. This is very similar to the board net stabilization case in terms of design, but the supercapacitors are only used if the power is lost to the system, as might be the case if there is an accident which disconnects the main battery or the main battery is fully depleted. Supercapacitors provide power to get the vehicle to safety, for example, to the side of the road. The designs are also similar to the board net stabilization designs, but typically used at lower power for longer discharge times. It's still on the 48 volt bus, so designs typically use 18 cells again in the 400 farad range. Supercapacitors are selected for their wide temperature range, allowing them to be placed in different locations wherever space may be available in the car. The long lifetime, while being constantly charged, ensures that they never need replacing. With supercapacitors being used more and more in cars, I thought I'd talk about a couple of general applications. These are not specific to 48-volt systems, but to EVs in general. Functions like door locks, emergency communications, and lighting all need to function for safety. But the high voltage battery will be disconnected in an accident, as discussed earlier. Small supercapacitors are used in many of these applications at point of use. So they sit on the door lock mechanisms or in the roof where radios transmit data for GPS and sensors during an accident. These are much smaller and lower power requirements, so it's typically just 2 cells required to reach 5-volt operating systems. These are also smaller cells than the 48-volt applications because of the power levels. The communications application might be just 3 to 10 farad cells, and again, 2 in series, while the door locks are typically 10 farads, maybe up to as much as 100 farads. The size in this case depends on the OEM and how many times they need to unlock a door on one charge, as well as how long between charges they need to last, the so-called airport parking use case. In summary, supercapacitors are now commonplace in automotive designs. With 48-volt systems gaining in popularity, supercapacitors are also being used in these applications. They're distributed around the vehicle wherever peak power or backup power may be needed for high current users. This can be on the board net to stabilize the minimum voltage, can be as backup power, or dedicated to something like active suspension. The wide operating temperature, safety, lifetime, and environmental features make them more and more attractive to use in new applications. I encourage you to visit our website at eaton.com/supercapacitors to learn more.
Thank you, Jason. Good day, everyone. My name is Elon Brown, and I work for Eaton as Global Product Manager for circuit protection within our electronics division. The presentation topic is specifying high voltage fuses for EV applications. Let's get started. Today, I'll be discussing a critical component in electric vehicles, high voltage fuses, and how we specify them. First off, it's useful to understand the difference between the low voltage and high voltage systems in EVs. Low voltage systems typically operate between 12 and 48 volts DC. You'll find these in both combustion engine cars and hybrid EVs. Think of the traditional car stuff here: lighting, infotainment, HVAC controls, engine control units, safety systems. That's all usually on the 12 volt side. For mild hybrids or vehicles with stop-start features, they might use 48 volts DC. Circuit protection here is generally pretty simple, using standard blade fuses and relays. Now the high voltage systems, this is where things get interesting for full battery electric vehicles or BEVs. These systems run much higher voltages, anywhere from 400 volts up to 1000 volts DC. Because of these higher voltages, the circuit protection needs to be more advanced, focusing heavily on enhanced safety and reliability. So, what exactly are these high voltage fuses protecting in a BEV? The main power comes from the high voltage battery, which again can be anywhere from 400 volts to 1000 volts. This battery powers some big components like the electric motor, the onboard charger, the main HVAC system, and the DC to DC converter that steps down the high voltage for the 12 volt system. We also need protection for DC aux circuits. This includes things like the PTC cabin heater and the AC compressor, which draw significant power. And of course, protection is needed for the entire onboard charging system, covering everything from plugging into the grid to charging the battery. The EV market is constantly evolving, and that's creating new challenges for circuit protection. What's driving this? Customers want longer driving range, faster charging, and lower costs. To meet these demands, manufacturers are using larger batteries and pushing for higher system voltages. Electrifying larger vehicles also requires higher power levels. All of this directly impacts the demands on our circuit protection, specifically leading to requirements for handling higher operating currents, higher voltage systems, and crucially, higher fault currents. We'll look at each of these impacts in a bit more detail. Let's start with operating current. With the move to larger batteries and higher power, the continuous operating currents in EV circuits are going up. The big impact here is that vehicle manufacturers are being forced to look at more advanced circuit protection solutions, especially for those higher current applications. It's not just fuses anymore. We're seeing advanced solutions that might include fuses plus triggerable devices like pyro switches or circuit breakers. Next, system voltage. As we mentioned, pack voltages are increasing, pushing towards and beyond the 800 volt mark. Why are they doing this? Higher voltage allows for equal power delivery at lower currents, which means you can use thinner wires. Thinner wire means less weight and easier packaging, which is a win for vehicle design. Higher voltage also enables faster charging times because you can push more power without excessively high current. Looking ahead to 2031, estimates suggest that systems operating at 800 plus volts could make up between 15% and 25% of the market. This means components like fuses, pyro switches, breakers, contactors, and even the wiring itself within power distribution units must be rated for 800 plus volts. Finally, let's talk about fault current. Battery pack sizes are getting bigger to give EVs that longer range people want. The downside, from a protection perspective, is that as the battery pack size increases, the available fault current in a short circuit situation also increases significantly. This has a major impact. OEMs now need overcurrent protection devices, like fuses, that can reliably interrupt very high fault currents, potentially in the range of 20,000 to 30,000 amps. Given these increasing demands, it's clear that EV fuses aren't just standard industrial fuses. There are key differences, especially in requirements and testing. While both might be ISO 9001 certified, EV fuses typically require the automotive-specific IATF 16949 certification. Industrial fuses are certified to standards like UL or IEC, but EV fuses need certifications to automotive standards such as AEC Q200 or ISO 8820. The reliability testing is also much more stringent for EV fuses. Think vibration, temperature, humidity cycling, thermal shock, current cycle endurance, and high temperature endurance, all of which are required for EV fuses, but not required for industrial ones. In terms of application, EV fuses handle much higher voltages, up to 1,000 volts compared to around 500 volts for industrial. They also cover a much wider range of currents from sub-amp sensing fuses up to 600 amps or more for circuits and fast charging. So what EV fuses are out there? Manufacturers offer a wide range of fuses for different EV applications. For smaller aux loads or onboard chargers less than 12 kilowatts, you might see fuses in the 0.1 to 3 amp range, often used for high voltage sensing. For larger OBCs and auxiliaries, the range is more like 5 to 175 amps. And for the main battery protection in DC fast charging circuits, you're looking at much higher ratings from 150 amps all the way up to 600 amps or even more. These fuses come in various voltage ratings too, from 500 volts up to 1,000 volts. Different current and voltage ratings are available, often with overlapping sizes to give designers flexibility. Mounting options are also varied, including surface mount, radial or through-hole for PCBs, and larger bolt-down tab mounts. Some manufacturers like Eaton even offer custom geometry if needed. Okay, simple question, but fundamental. Why do we use fuses in the first place? At its core, a fuse is an overcurrent protection device. Its main job is to prevent fires and protect expensive equipment from electrical faults. There are generally two types of faults we're concerned with: short circuits and overload faults. So why a fuse specifically? The key benefit is isolation of the fault. In a short circuit, fuses are designed to quickly limit the amount of energy let through and limit the peak current. We call those current limiting fuses. For overload faults, fuses protect the wiring or act as a backup if the primary protection system fails to open the circuit. This graphic shows a typical industrial fuse in blue and an EV fuse in red, illustrating their time current performance differences. The key takeaway here is that EV fuses are designed for much faster and more precise interruption performance compared to standard industrial fuses, especially under fault conditions. Let's quickly look inside a fuse. You have the N terminals. These connect the fuse into the circuit. We want high electrical and thermal conductivity here, plus good mechanical strength. The tube body is usually ceramic or filler material. It needs high thermal conductivity and dielectric and mechanical strength. The heart of the fuse is the fuse link. This is typically made of copper or silver. It has intentionally narrow sections called neck down areas, which are designed to melt precisely at high current levels. EV fuse links have special designs to improve cycle life and reliability given the demanding conditions. Inside the body, you'll find a filler, typically silica sand. The purity and quantity of this sand are absolutely critical for effectively interrupting high voltage DC faults. So how does this all work? Fuses are thermal devices. They essentially act as a small resistance in the circuit. We're talking fractions of an ohm, like 0.1 to 10 milliohms. Under normal load conditions, current flows through the fuse link and it heats up slightly. This heat is dissipated through the body and the N terminals, and the fuse reaches a stable operating temperature. Now, if a short circuit condition occurs, the current spikes dramatically. This rapid increase in current causes the fuse element's temperature to rise very quickly, reaching the melting point of the silver or copper material. The weak points, those neck down areas, melt first. Silver, for instance, melts around 961 degrees C. When the link melts, arcs form across the gaps. These arcs generate an arc voltage. This arc voltage actually works against the system voltage, helping to force the current to reduce. The arcs then interact with the silica sand filler, and this interaction turns the sand into a glass-like material called fulgurite. Fulgurite is a high resistance insulator, and it further helps to quench the arc and force the current down to zero, clearing the fault. This graph, the time current curve, is key to understanding how a fuse performs. It shows you how long it takes for a fuse to open or blow at a specific current level. To read it, you find the potential fault current on the bottom, the x-axis. You move straight up until you hit the curve for the fuse's amp rating you're looking at. Then you move left to the side, the y-axis, to see the time it takes for that fuse to open at that fault current. For instance, if you have a 60 amp fuse and the fault current hits 300 amps, it will take 0.4 seconds to open based on the curve. We use these curves to check coordination, making sure the fuse opens fast enough to protect the components downstream. Fuse selection can be challenging because many factors influence how a fuse performs and lasts in a real-world application. The driver profile is huge. Is it a highway car, city car, frequent acceleration and deceleration? How are the aux loads used? All this changes the load patterns the fuse sees. The physical environment matters too. Enclosure and conductor size, ventilation and cooling, and the ambient temperature around the fuse. These affect how well the fuse can dissipate heat. Specifying a fuse is really a balancing act. There's an inverse relationship between its ability to interrupt a short circuit quickly and reliably and its overall durability and reliability over time. Ultimately, fuse selection is a trade-off. You want better protection, but you also need better reliability. Finding the right balance is key. Getting the fuse size right is crucial. If the fuse is too small, it can trip too fast. This might be a nuisance trip under normal operating conditions, or worse, it could compromise safety if it fails prematurely. If the fuse is too large, it trips too slow. This is a major safety issue because it might not open before the fault current damages other expensive components. The big challenge here is that customer driving habits and environments are incredibly varied, even infinite in possibility, and all these scenarios influence the optimal fuse choice. Again, it's the trade-off between better protection and better reliability. The goal is typically to select a fuse that can provide a minimum service life of 10 years. Environmental factors like cooling, conductor size, and ambient temp heavily influence this. Let's walk through a typical process for selecting an EV fuse. Step 1, rated voltage. You need to select a fuse voltage rating that is greater than or equal to the maximum potential system voltage, and specifically confirm it has an adequate DC voltage rating. Step 2, rated current. You'll select an initial nominal current rating based on the continuous operating or RMS current in the circuit. Crucially, you then need to apply a derating process. This adjusts the fuse rating based on environmental and operational correction factors. We'll dive into derating soon. Step 3, size and mounting type. Once you have the voltage and derated current requirements, you choose the physical size and mounting style that fits the application. Step 4, coordination. You must check that the fuse will blow before other downstream components like connectors, wires, or contactors sustaining damage. This is done using time current curves. Step 5, influence of overloads. Here we account for potential overloads or inrush currents that might be present in the load profile. And then finally, step 6, cyclic loading. Here we consider the effects of repetitive variations in current on the fuse element's fatigue and lifespan. Let's circle back to selecting the rated voltage. As mentioned, the fuse voltage must be greater than or equal to the maximum potential system voltage. It's also vital to confirm that the fuse has an adequate DC voltage rating, as DC interruption is more challenging than AC. Speaking of voltage, fuses in series should generally be avoided. It's not a recommended way to increase the effective fuse voltage rating. However, using fuses in parallel is acceptable in EV applications for increasing the rated current capacity. It's not standard practice, but it can be used in EVs. If you do put fuses in parallel, only use fuses of the exact same type or part number. And importantly, mount them so that the current and heat distribution to the connections is equal across all parallel fuses. Remember, the fuse voltage rating needs to exceed the system voltage even at the battery's maximum state of charge. Derating is a critical concept in EV fuse selection. What is it? Fuse derating is the practice of reducing the fuse's nominal current rating to ensure it works reliably in the challenging EV environment. Why do we do it? EVs operate under tough conditions: high temperatures, vibration, humidity, and fluctuating electrical loads. These factors can cause a fuse to open prematurely at a current below its listed rating. Derating accounts for this by making you choose a fuse with a higher nominal current rating than the absolute maximum current you expect in the circuit. The core concept is captured in the derating equation. You calculate a minimum required fuse rating, IN, based on the continuous current divided by a correction factor. The correction factor is a product of several individual derating factors that account for specific environmental conditions. These correction factors reduce the fuse's rated current capacity to account for the harsh automotive environment compared to standard industrial uses. Here are the main factors. K sub T accounts for the maximum ambient temperature the fuse will experience. K sub E relates to thermal connection, influenced by things like wire size. K sub V, for cooling air, accounts for whether there's active airflow or not. K sub F, a frequency correction factor relevant for AC circuits, less critically for purely DC EV systems. K sub A corrects for high altitude operation. K sub X applies if the fuse is enclosed in a confined space. Because EV fuses are in these demanding environments, they must be derated based on the specific application requirements. So, where do you get the values for these K factors? You identify which factors are relevant to your specific application based on the vehicle's operating conditions. Then you consult derating factors provided by the fuse manufacturer. These charts give you the appropriate correction factor value based on the specific environmental condition. For example, the chart shown here is for the maximum ambient temperature, K sub T. You find your maximum expected temperature on the bottom and read up to find the corresponding K sub T value. You can typically find these charts on the fuse datasheet or in the manufacturer's application guide. Let's walk through a quick example to make this more clear. Suppose we need a fuse for an EV aux load like a PTC heater. The continuous current, I sub B, is 30 amps. Maximum ambient temperature is 60 degrees C. The fuse is in a small enclosure with no ventilation and is connected to cabling, which is 15 millimeters squared in cross-sectional area. Maximum altitude is 2,500 meters. Nominal system voltage is 800 volts DC with a potential 10% overcharge. Maximum available fault current is 22,000 amps. Okay, let's apply the factors we just talked about. I sub B is our 30 amp continuous current. K sub T for 60 degrees C is 0.8. For K sub E, the thermal connection derating factor, the example calculates current density based on the 15 millimeter squared wire and 30 amps. The recommended guideline is 1.3 amps per millimeter squared. Based on this calculation, the 15 millimeter square wire is about 52% of the recommended size, leading to a K sub E of 0.85 in this example. Since there's no air cooling specified, K sub V is 1.0. Its DC current, so K sub F is 1. For the 2,500 meter altitude, K sub A is 0.97, and because it's a closed small space, we apply an additional K sub X of 0.8. Now we plug these values into the derating equation, and the result shows that the required fuse rating I sub N is greater than or equal to the continuous current divided by the product of all the subfactors. And then doing the math for this example, the equation tells us that the fuse rating needs to be greater than or equal to 1.89 times the continuous current. So IN is greater than 1.89 times 30 amps, which is 56.7 amps. We then round up to the nearest available standard fuse rating, which in this case is 60 amps. Now that we have our voltage and current requirements, we can select the fuse. First, the voltage. The system is 800 volts DC with a potential 10% overcharge, meaning the max voltage could reach 880 volts DC. Therefore, we need to choose a fuse rated for at least 880 volts DC. A 1000 volt fuse is the appropriate choice. Next, the current. Our derating calculation indicated we need a fuse rated at 57 amps or higher, so we selected a 60 amp rating. Manufacturers offer multiple package options at different ratings. For a 60 amp 1000 volt fuse, there are various package options available. In this case, we choose the smallest offering from Eaton, which is 14 millimeters in diameter, and we have the ability to go up to a 70 amp rating in the same package in the future if we need to derate further. Moving on to finalizing the selection, we look at the mounting type. Checking the datasheet for our chosen fuse, it offers options like PCB mount or bolt-down terminals. Since this fuse is connecting to cabling and bus bars, the bolt-down version is the right choice for the application. Finally, and very importantly, we confirm the fuse's breaking capacity. This is the maximum fault current the fuse can safely interrupt. In our example, the maximum available fault current was 22,000 amps. We must confirm that the selected 60 amp 1000 volt bolt down fuse has a breaking capacity that exceeds this 22,000 amp fault current, which it does given the 50 kA rating from the datasheet. A fuse's main role is providing overcurrent protection to everything connected after it in the circuit. Its job is to open or blow quickly enough during a fault so that not enough current passes through to damage components like wires, contactors, or other devices. When the fuse clears the fault before these downstream components are damaged, we say the fuse is coordinated. We verify coordination by looking at the time current curve again. We superimpose the fuse's time current curve with the damage curve of the downstream component. Coordination exists if the fuse curve is always below and to the left of the component damage curve, meaning that the fuse operates faster at any given current level than it takes to damage the component. There needs to be clear separation between the two curves. Beyond just fault currents, we also need to consider the influence of overloads and impulse loads. Overloads, like sustained high power draw, or inrush currents, which are brief high current spikes when equipment turns on, can occur in aux loads and even motor drive systems. These loads must be accounted for to ensure the fuse lasts for its intended service life. The fuse needs to be tough enough to withstand these expected inrush currents without failing until the current settles back down to normal operating levels. However, very high peaks, even if brief, can stress the fuse element and reduce its overall lifespan. We typically categorize overload time durations into two groups, those longer than 1 second and shorter than 1 second, which we call impulse loads. To evaluate if a fuse can handle overloads, we look at its time current curve and apply a percent factor. The maximum overload current, Imax, the fuse can withstand for a given duration, T, is typically less than the actual melting current, I sub T, shown on the time current curve for that duration. This accounts for cycling stress and other factors. Here's a quick example using our previously selected 60 amp fuse. Let's say we need to check if it can withstand a 60-second overload that peaks at 150% of the continuous current. From the time current curve for the 60 amp fuse, we find the melting current IT at the 60-second point. In this example, it's 110 amps. Using a percentage factor of 60% from our table, the maximum allowable overload current, Imax, for 60 seconds is calculated as 0.6 times 110 amps, which is 66 amps. So for a 60 amp fuse, the maximum sustainable overload for 60 seconds is 66 amps. This means the fuse is suitable as long as the actual 60-second overloads in the circuit don't exceed 66 amps. This brings us to another factor affecting fuse life, cyclic loading. Cyclic loading means the current isn't constant. It varies regularly or irregularly. These variations cause the fuse element's temperature to constantly change. Repeated heating and cooling, particularly at the restrictions or narrow points of the element, can cause metal fatigue over time. Think of bending a paperclip back and forth. Eventually, it breaks. This repetitive stress from cyclic loading can lead to the fuse failing prematurely, even if the current never reaches levels that would cause it to blow immediately. Given the complexity of real-world EV drive cycles and the impact of cyclic loading, how do we ensure a fuse will last? Eaton offers EV fuse simulation capabilities. Customers provide their application's specific load profile, plus things like busbar sizes, ambient temperature, and the expected current patterns over time. Eaton can then use analysis and simulation tools to model how the fuse will behave under these conditions and estimate its cycle life. The big benefit of simulation is that it helps confirm the fuse selection before costly and time-consuming physical validation testing. It enhances confidence and can shorten the project timeline. Custom drive and charging profiles can be simulated against the fuse's known fatigue characteristics to help suggest the required fuse ratings for a specific application. Physical testing is still essential, of course, following standards like JASO D622, ISO 8820, or LV 124, along with any custom requirements from the OEM. So, to wrap up based on what we've covered, selecting the right high voltage fuse for an EV is a detailed process that goes way beyond just picking a current rating. It requires careful consideration of voltage, current, fault current, and the challenging operating environment. Derating based on environmental factors is absolutely critical for ensuring reliability and preventing nuisance trips or premature failure. And importantly, accounting for dynamic loads such as overloads and cyclic loading through methods like simulation and testing is essential to ensure the fuse provides the required lifespan in real-world EV applications. This careful selection process ensures the fuse can do its vital job protecting sensitive components and, most importantly, ensuring safety. For additional resources, like links to datasheets, 3D models, block diagrams, and our EV Fuse application guide, please visit our website at the link below. Here, you'll also find links to our free sample center and contact information to get in touch with our team directly. With that, I'll hand things back to EE Power and wrap things up.
All right. Thank you, Jason and Elon, for that, really detailed presentation. I find it fascinating to see the complexity and the variety of the fuse products that are available today. We've already got several great questions, but there's still time to submit your questions, so go ahead and do that. Elon, are you ready to answer some of these questions?
Yeah, for sure, Dale.
All right. The first one here is asked by Matthew, and he's asking, what components would you expect to damage in the event of the trip delay time is not fast enough?
Good question. So this question ties into the coordination aspect of fuse design that we touched on in the presentation. The fuse has to open before damage is sustained to anything downstream. So this would really be whatever's downstream of